Hello, friends. Let's talk about harmonic waves. What a harmonic wave is, otherwise known as a standing wave, is when you have you can do it in 2 or 3 dimensions, but really we're going to do it in 1D. And one-dimensional wave, recall that the velocity of a wave is the square root of the tension over the linear density. The linear density is mass per length. So let's say I have a slinky that has a length L and a mass M, and therefore linear density is mass over length. It also has a tension pulling inward, which is going to create a velocity. If I create a little pulse here, it's going to create a velocity moving forward through the slinky. That is going to then bounce back and forth, and the time it takes to go back and forth will be the distance 2L over the velocity v. And if I match the frequency input to the time of reflection, you get what's called resonance. So I'm going to do that experiment. Imagine a wave going back and forth. Boom, 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 boom. Right? If you input the frequency like this, so it matches the motion back and forth, it's like pushing someone on a swing, right? At just the right moment. So when the wave comes back, the input inputs new resonance or inputs new input. It makes it right. It makes the wave go down when the wave hits again, or it makes the wave go up when it hits again. So if you match the frequency to the velocity back and forth to that time, you're going to get resonance. If you don't, imagine pushing someone on a swing and you do it too soon or too late, the frequency of your input doesn't match that timing of their motion. Those are two separate things. The input is different than the motion of the wave back and forth. But if you match them, you get resonance. If you don't and you're on the swing, you're gonna get all herky-jerkied, and it's just gonna cause this like disordered, like not smooth, destructive motion that's just gonna look weird and feel disordered. I don't know. I don't know if I want to use the word chaotic because it's predictable. It's not true chaos. True chaos is unpredictable, but it's not going to be harmonious. It's going to be destructive and wobbly and disordered. I'll use those words. Hold on. Is this working? It's working. We did it. So therefore, the frequency must be 1 divided by this. Because if you guys remember, frequency is cycles per second. So frequency is 1 divided by the time that you want it to take, right? Which means it's going to be, and we'll call this the first frequency because it turns out more than this works, V over 2L. And I'm going to write this formally on the next page because check this out. So the first harmonic, n equals 1, n is the number harmonic. What happens is when it resonates, it's literally just going to vibrate up and down. Like you have this vibrating up and down in place. It's a standing wave where technically you have a velocity going forward and you have a velocity going backward, but they're interfering with each other such that it resonates like this. So it really just resonates like this, up and down and up and down at some frequency. It's also the number of half wavelengths, which I call humps, right? So this is the length of the rope. In the first harmonic, 1/2 of the wavelength is the length of the rope. So therefore, the wavelength is 2L. And a quick examination can confirm that clearly this is a full wavelength here. Full wavelength is 2L, which means that the frequency, don't forget frequency is, what is it? V over lambda in general, right? Careful, this is not cause and effect. The rules still apply. F is still the input. V is still dependent on the medium, right? And lambda is still the result, the outcome, right? But what we're doing now is we have to restrict lambda so that it resonates in place. So lambda is restricted by L because we need the wavelength to match the length or some fraction of the length or some multiple of the length of the slinky so that we have a full half wavelength matching the geometry. That will also create the timing match that I was just referring to. That if you match the amount of time this takes to go back and forth, boom, boom, then what you're actually doing is matching the wavelength. Because if you remember, a wavelength is one period, right? Which is the distance traveled, right? Uh, in the time t. And the frequency is 1 over that, 1 over the period, right? So cool. Let's just go back to this. So the whole point is this is one length, this is a half wavelength, lambda is restricted. So we have to therefore restrict, therefore F is restricted to create harmony. Because I can put in any frequency I want. I can make a disharmonious situation. I can wobble this any way I want, and I can just make it all disharmonious. But if I want harmony, I need to look at the geometry, and therefore I need to only input V over 2L, and I will get this situation right here. This is called the fundamental. The fundamental frequency. Boom. Obviously, you guys can pause and rewind if you need. I'm just going to flow. So the second harmonic is where you fit 2 humps in. So you get 2 half wavelengths equaling the length of the rope. Clearly, the length of the rope is the wavelength here. So what we end up seeing is that this is half the fundamental wavelength. So therefore, the second harmonic frequency is just going to be V over L, which is 2 times the fundamental. The wavelength got halved, which means the frequency got doubled. Boom. Don't overthink it, right? The velocity is the same velocity, same medium. We're still interfering with itself. It's reflecting and interfering with itself. That's it. The third, you just got to draw it like this. Boom, boom, boom. It vibrates up and down. This is vibrating up and down at 2 F2. This is vibrating up and down at F3. What's the wavelength here? Clearly, the wavelength here is 2/3 the length, right? Which makes sense because 3 half wavelengths are in the length of the rope, right? So if I solve for lambda 3, I get 2/3 L, which is lambda 1 over 3. And if lambda got multiplied by 1/3, frequency got tripled. So therefore, the frequency of the third harmonic is 3 times the fundamental frequency. Boom. So for the nth harmonic frequency, what we get for a general n, right? So n is 10, n is 100, n is 5, right? Whatever it is, what we see is that the nth harmonic wavelength is 2L over n, and the nth harmonic frequency is n times v over 2L. But remember, the fundamental is v over 2L. Please know it by this name, by the way. Fundamental frequency. Boom. Put that in a little bubble, put this in a box, put this in a box. But really, we want to know this as n times the fundamental. It's so easy. So if n is 10 and the fundamental frequency is 2 hertz, then the 10th harmonic frequency will be 20 hertz, right? 10 times the fundamental. And it'll look like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And these will be vibrating up and down at 20 hertz. And this is the length of our slinky, which is really hard to do. It's really hard to create this many, but you just need to shake it 10 times as fast as the fundamental, and you're going to get that. That's it. Practice in class, pretty easy. I could go over more examples, but that's the theory. So as long as you have that down, honestly, you should be able to get it. Just don't forget the velocity equation determines the velocity, but you guys know how to do that. See you guys soon.